Okay, so on this one it's very similar to the previous one. So it's still rotationally symmetric around the z-axis. The equation for the graph looks very similar. Z equals, this time, e to the negative x squared plus y squared. And the only difference is that when you look in this half plane, and I'm going to look in the same half plane because as well, just to connect to the previous discussion. In that green half plane, it becomes z equals e to the negative y squared. And you just have to understand what that curve looks like. And again, here you have to think about single variable calculus and what do we know in certain cases. And so let's plug in some points. When y is equal to 0, still 1. But now, as y increases, negative y squared becomes negative, and I have e to the power of a negative number, which is going to get smaller than 1. So it starts to decrease. All right, now does it just keep decreasing forever? Well, no. See, the thing is, it's an exponential, so it's always positive. So it decreases, but it never goes negative, so it has to kind of level off like that, right? And furthermore, it levels off at 0 because take the limit, single variable limits, etc., blah, blah, and the limit is 0, so it's got to look kind of like this. Well, it looks kind of like this. Yeah. Does that make sense? So now you have the artistic challenge of how do we draw what it looks like when that rotates around the z-axis. And appealing to your geometric intuition, it makes a little hill. Right, so how do you draw a hill? And this is a situation where it helps to have done this a few times in the past, and I'll show you how I draw a hill. Well, there's different little tricks, but you can just, I'm going to draw this to indicate that asymptotically, as you get further away from the origin, it becomes kind of flat, and then there's just kind of a hill, right? And it's not a perfect drawing, but with if with this being drawn as well, if you put both drawings on the page, and it's very clear what this curve is, and you're indicating that you're rotating around the z-axis, and then it's clear what you mean by this. Yeah.
But wouldn't the tails of the hill not be less than y equals 0?
Yeah, no, they're not. Yeah, this is intended to be a little hill that's sitting sort of on top of the xy plane. So you're worried about like these points here. That's not below the y-axis. Okay. That's just closer than the y-axis. It's toward us at the y-axis.
But it's
still above the xy plane.
Okay.
Yeah. So it's not a perfect picture, right? I mean, if you want to give it a little dimension by doing something like that makes it look a little more three-dimensional. You could even, if you want, kind of do something like that. I want to make it more clearly 3D, but yeah.
So would the tails ever hit 0?
No, but the value of the function is never 0. Okay. Right. And so, by the way, I mean, the way that you, when you're drawing something, if you're drawing a two-dimensional surface with a one-dimensional pencil, right, a pencil that makes one-dimensional curves, you're not going to make a perfect picture. So your best case scenario is simply to try to trick the viewer's eye, right? And so you'll notice I didn't draw. I mean, this technically keeps going up to infinity, but I feel like that's, my imagination can kind of see that still, right? And it's not really necessary as part of the picture. So exactly what you draw is, you have to make some sort of artistic choices as to what is going to what that I might draw is doing more good than bad, right? Is this actually helping the eye see something that is more valuable than the confusion and clutter that it's adding to the page, right? And so there's a certain amount of experience in that. And there's certain little drawing tricks that you learn from time to time. When I was in grad school, I found myself in a situation where I had to draw donuts a lot. So I learned how to draw donuts really well. There you go, donut. Right? I didn't think that up on my own. Somebody showed that to me, right? And it's like, oh wow, that totally works. Oh, I kind of get the. Oh, okay. And then you memorize that little trick, and then now you don't ever have to worry about that ever again. Yeah.
So, do you think that it's easier just when you're drawing a picture and you're rotating around the z-axis, so it's on the xy plane, to actually like draw out the xy plane like you did?
Oh, it's I don't want to say always or never, right? But in this case, I think this passes the does it do more good than bad test.
When
yeah.
would it do more bad than good?
Oh gosh. I can't dream something up. I'm not.
It's a very.
Yeah, it's hard to.
Maybe just like doing it. If it doesn't work, just erase it.
Yeah, that's right. You try things, right? And so when I draw, like the pictures that I drew in the textbook, these are all hand drawn, pencil, right? And there are a lot of eraser marks, and there's a lot of crumpled pieces of paper in a landfill somewhere that represent my first, second, third, and fourth attempts at what eventually made it into the book, right? So yeah, you gotta try, fail, learn from your mistake, try again, and then get increasingly better pictures. Yeah. Yes.
Can I interpret the function in question 4 as like a reflection of the one?
So yeah, no, that's what somebody in the back asked. So it's not a reflection because remember the picture that we drew earlier was something more like that, right? And so it's not a reflection because this red surface from question 3 goes up to infinity. The blue curve does not go down to negative infinity. Right? So they're not reflections of each other. And the reason for that is that the minus sign here, that minus sign is inside of the exponential as opposed to outside of the exponential. If it was outside of the exponential, then yeah, it would be a reflection. Yep. Everybody good on this question?
Yeah.
Okay. Let's stop it here.